start again with the course. Here I write the main theorem that we proved yesterday, and which gives us a classification of the simple module over an algebra with triangular decomposition in terms of the simple modules over the T algebra, over the algebra here in of the datum. So what we proved is if A is an algebra with triangular decomposition, and if we take a complex set of non-isomorphic T modules, then these L lambda, which are the simple module, which are the head of the proper standard modules, give us a complex set of non-isomorphic simple A modules. And this is is one of the first steps in order to study the representation theory of an algebra, is to study or have a classification of the simple modules. That is very good information for us. And let me recall how we construct these L lambdas. This simple model we constructed in the following way. We start from the simple modules over T. Here, take a lambda, or one of these in the lambda, and then we went to the yes, it's also simple, to the simples in the category of B plus modules using the inflation. And then we went to the category of module over A using the induction function. We take the proper standard module as the inducing from B plus inflation. And then what we proved is that the head of this proper standard model give us a simple model. Take a lambda equal to the head of the proper standard model. I am come back. Okay. So here is the path that we follow. You see, we go from T to B plus, and then to A, and again A taking the head. And somebody could ask as if there is certain symmetry in the category, and somebody can ask, one could ask if we can go instead to take B plus, if what happens if we take we go to B minus. It's possible. It's possible to go here. That is, it could be a very natural question. Let me put it more explicitly. Can we replace B plus by B minus? That is a natural question. Can we do the same using B minus instead of B plus? And the answer is not always. And for this, not always, this is the example, the exercise 4 that which is in the exercise. Yeah, we can put C exercise 4. And not always, and we can be more precisely, and it is only if we have this this property. If the tensor product between A plus T and A minus give as using the multiplication is also an isomorphism of vector space. Here the difference between the original definition of triangular decomposition is that we changed we treated A minus and A plus. Okay. So if this happens, then we can proceed in the same way. So we didn't to prove nothing. We just using the theorem that we have proved, and we will obtain another description of the simple model of A. And that is the what I tried you see in the exercise 5 of the exercise that I sent you yesterday. What happened? Oh. Okay. Okay, we continue, and instead what we will do later in some minutes is that we in order to explode or to use that this whole algebra that we have A minus, in order to use also B minus, we will introduce later the proper standard models, proper co-standard model. Instead, we can use proper co-standard model or co-standard. And we will define this later, but that's in order to give an introduction to the lesson of today and to see and recall what we did yesterday. Okay, but what we will do today is to analyze the structure of L lambda. In the first part of today, we will analyze the structure of L lambda as T model, which is the problem that I proposed yesterday at the end of the lesson. So for that, I need to introduce or recall what is the Grothendieck ring of an abelian category. So we will start now with a new section, the Grothendieck group. Of CF. I will recall what is this. Okay, and recall this is a group. This is an abelian group. This is abelian group generated by isomorphic classes of objects of module is here in the category of module over A, graded or ungraded. So we put the generator of this abelian group is we have one generator for each isomorphic class of modules. So it's a way to put together all the modules isomorphic and try as it were only one. And okay, we have all these. These are the generators of the group, and they certify this relation. Subject. This is the sum of the group. Oh, sorry. Before the subject generated by this with the sum with the operation, which is the operation if you have two classes of objects, x and y, the sum of them is the direct sum, is the isomorphic class of the direct sum. And we pose a relation we will say that the class of y of x is equal to the class of y plus the class of zeta if and only if there exists a short exact sequence or in other words, if x is an extension of y and zeta. This is the Grothendieck group of this abelian category. For any abelian category, this Grothendieck group is defined in the same way. Why I introduce this? Okay, this is called also if we take the and we will denote K of CA. This is that. And analogous in the same way we define the Grothendieck group of the category of T modules. Yeah. Okay. Are you watching? You see, find this part? If you don't see it, let me know. Okay. And we I introduced this group because as we want to study the structure of the simple module over as T module, it's the same that study the representative of a module in the Grothendieck group. So I will introduce a new definition. The following: if M is a module over A, the character of M is the following. We will denote CH of M. It is the sum over lambda in lambda. This I recall lambda, big lambda is a set. It's a complex set of non-isomorphic simple T modules, and this will be the sum over lambda of M lambda. This element will live in the Grothendieck group of the category of T modules, and where M lambda, this is an integer which usually is denoted in this way: brackets between brackets M and lambda, and this is the numbers of composition factors of M isomorphic to lambda. And now I will recall with what is the composition factor. recall that. Let me see if I have space. I will recall that this is for any module M admits a filtration in the category of modules, A modules, such that this filtration satisfies that when we quotient every of these submodule, we obtain a simple model, such that continues here. Such that when you take the quotient, this is isomorphic to L lambda y. So is it no? Here I want isomorphic to lambda y for some lambda. In lambda. And this is what is called a composition factor. So in other words, the character of M encodes the structure of M as a T model, more or less, because yes, that is what we can do to encode to put all the information of this module as T module. We can form this character and we encode this information there in this which is an element in the routing the group of the category. There is some question. Yes. Okay. Let me know. Yeah, because this yeah, you are right. Sorry here sorry, could you, yes, you are right here. This filtration is in as T models. Thank you for the question. Here I take the M is an A module, but when I consider the character, I see it as a T module and take the filtration in the category of T modules. Okay, well, thank you. And a remark is that there are cases, there are algebras with triangular decomposition for which L lambda, or the character of the simple module, are equal for lambda non-isomorphic to mu. So there are examples of algebra with triangular decomposition that when you take the character of this of the simple modules, you obtain the same. That means that the character is not too good to study the simple modules because we cannot distinguish them from the characters. And this happens because we are considered the category of ungraded modules. But now what this say us that it is not good to take the category of ungraded module, and we need to take the we will see in the category of graded module that the character is a good approximation to the simple modules. So instead to take this character, we will take the graded character. But I write now what it is. This is the same, but it's in the category of graded models. And before that, I will do some remark that actually I already mentioned this before. Let me make another remark. Okay. As t is equal to t0, is concentrated in degree 0. If m if we take a simple module in the category of graded T modules, then M is concentrated in a unique degree. Yeah, that is because T is concentrated in degree 0. If it is not the case, M will be decomposed in the direct sum of two components, and each of these components will be a T submodule because it's concentrated in degree 0, and then M will not be simple. So then M is isomorphic to lambda, and I will denote in this way, lambda z, for some lambda in lambda and d in theta in the integers. And with this notation, this means lambda This means this is the simple module, the graded simple module of the simple module, the simple Thiel module, lambda concentrated in degree d. So this is a new notation. This is what it means. And of course, lambda 0 is just lambda. Because we are considered lambda is in the category of models of ungraded model. Okay, and because of this, okay, we have that every simple model, every graded simple model over T is isomorphic to one model, to a model of this form, lambda and D, and that means that therefore the set lambda times integers is a complete set of non-isomorphic graded simple T models. Okay, we now are ready to introduce the graded character. If you have any question, you can write it in the chat. Okay, the graded character of a module, of a graded module over A is, it will be, we will denote ch dot is a sum over lambda and over E the integers of this element will be, these are integers, and we will put some T will be an indeterminate lambda. This is like a polynomial. This will this belong to the Grothendieck group of MT but with this indeterminated like a polynomial. So to be more precise, where m lambda y, this is this is so this number is defined as above. It is the number of composition factor of M which are isomorphic to lambda in degree y. So this is like in the category of graded T models. And T It's an indeterminate. So these are like polynomials in the no fix the here. If you have any question, you can ask. So these are the number of composition factor of M, which are isomorphic to lambda in degree I. Okay, we can write in other ways. You see, we can put all these together, and then we can write this in other form. Now I can. We can, instead of sum over all the integral, we sum only over lambda, and we can put all this information in a polynomial. P lambda where P lambda is the sum over integers of these numbers, and this is a polynomial, is a Laurent polynomial. For instance, we can, for instance, we can see more or less the form of the graded character of a simple model L lambda, and this will be equal to lambda multiplied by the polynomial of the t to the d. Okay, for instance, sorry. I will put just lambda. For instance, is lambda, then the graded character. So here I am considering lambda in degree 0, just concentrated in degree 0. This will be equal to the isomorphic class of lambda plus some plus something. Let me just to in order to another polynomials. Here mu. Sorry, this will do the sum over mu, where the degree of this polynomial, the degree of this polynomial Q is smaller than 0, which is the degree of lambda. This is by lemma, I think 3.9. Because when because of lemma 3.9, and also we made some remark yesterday that the homogeneous component of the simple model L lambda has in the top degree, in degree 0, we have lambda, and then we have everything will be of lower degree, and then here I put all these things in lower degree in this sum. So the graded character is in this way. We already saw this yesterday, but in other form. Instead to talk about graded character, we just mentioned we have mentioned that L lambda is isomorphic to lambda plus something as graded T model. So and now and this also this was the reason that we can we showed that the simple modules are different, and then we can see also in using the graded character that they are different. In other words, so the graded character distinguish oh, I don't remember how to write this. And detect different simple A models, graded A models. And moreover, there is a proposition that I don't prove, I will not prove, but you can solve in the paper of Bellamy and Thiel, and there is and using this proposition I propose, and also using just that you can prove it, and also see an exercise in that I send you. Well, the proposition say that if we see this function, the graded character as a function from the group, from the grothendieck group of the category of graded A module to the graded to the grothendieck group of the category of T modules were enlarged by T and T as polynomials. This map is injective. And that means that the graded character gives us very good information about the structure of a modules, because using that this function is injective, we can distinguish the object, or we can deduce, for instance, from the category from the graded character, we can deduce the composition factors. Corollary. From the graded character of E, we can read the composition factors of M. Now in the category of graded A models. Here is okay, graded of A. Not as before where I made a mistake. Here is graded of E. And this is an exercise. Maybe it's not in the version that I sent you yesterday, but in a new version of the exercise will be this exercise 6 or 7. There is some question So in conclusion, this graded character is what we are looking for before when I say, well, try to investigate the structure of a simple module as a tree module, and this is the way to study his structure using the graded characters. So, a question. Yeah, I can. Conclusion. We have a classification of graded simples and modules in order to obtain more information of them. We could try to compute the graded characters for all lambda. And this is we don't analyze. We will not solve this question in general because this graded the algebra A could be very different. But this is most of the it is a central problem in Lie theory to compute this graded character when the algebra with triangular decomposition you consider the enveloping Lie algebra. This is a very important problem in that subject, and we can try to in order to obtain more information about the category of your favorite algebra with triangular decomposition. Once we have a classification of the simple model, the next step is to try to compute the graded characters, and this is good information because of this the injectivity of this map that I mentioned before. We will introduce these proper co-standard models. We will give just the definition and to emphasize that they satisfy similar properties that the standard models, and they are important because they explode. We can explode with them this symmetry of on the algebra with triangular decomposition. And for instance, the most important is what we will prove later then, which is the Brouwer reciprocity. And for proving that, we will use the proper and the co-standard, the standard model and co-standard models. And maybe we will prove this tomorrow, but we will start the path to there now today. I will start a new section, proper co-standard models. These are more or less the dual of the proper standard models, but we need some technical issues before to introduce it. So let me give you some notation. First, we still have a lambda as before. And we will denote A of, this is the opposite algebra, is the opposite algebra of A. That means that the multiplication between two elements of A is equal to multiply them twisted in the other side around with a different grading, with the grading the homogeneous component of degree I is equal to the homogeneous component of A minus I. And the other thing that I need to introduce is if M is a graded module, then we define M dual, which is dual the space of Hopf, the linear morphism from M to the field, and this is a module over the opposite algebra in the following way. With action A acting in F. This is the linear function obtained by applying F to A acting in F. And the grading of this space the homogeneous component of degree I is equal to the linear maps from M to the field, such that they kill the other homogeneous component of M. And this is isomorphic to the dual of the homogeneous component of degree I. Okay. And this give a functor. This give a functor from the category of A module, graded A modules, to the category of graded modules over the opposite algebra. And in particular, dualizing give a bijection between the simple objects. Yeah, some question about this notation of definition? And for what is important, this definition is we have this lemma. Five. Say that if A is an algebra with triangular decomposition then the opposite algebra is an algebra with triangular decomposition T of, which is, we have to put in the now the opposite part, the negative part will be the opposite, the positive, T will be T of. Sorry. This is okay. So the opposite algebra is algebra with triangular decomposition, where we have to interchange the roles of the algebra. Now the positive part will be the negative part, and the negative part will be the positive part. This is because how we have defined the opposite algebra. In the middle, we still have T, but with the opposite multiplication. And we will use this algebra and this triangular decomposition in order to define the proper co-standard models. There is some question? Definition. So we will now I will define the proper standard, the proper co-standard. We define nabla bar is a functor from, which is more precisely, it is the proper we will see. Nabla is the functor which first dualize, then take the standard model, and then dualize again. And this go from the category of T modules to the category of A modules. Just in a minute, I will be more explicit, but let me say before that, we will call nabla M. We call this is the proper co-standard model. Standard model of M. So these are the proper co-standard model. Now I will be more explicit about this construction, because this could be a little bit confused. So more explicitly, we first know that if we take, I will apply this functor each one in each step in order to see how this nabla M looks like. So we start with the module over T, and then we first have to apply the dual. So M dual, because of the notation of the beginning, M dual is a module over the opposite algebra of T. We then have to apply the proper standard model. Which is more explicitly, because we know the proper standard model, you see, go from the category of the module over the opposite of T to the category now of module over the opposite of the algebra A. and this is A op, tensor, B op, B plus op, no, B minus op, which is the positive part of the positive algebra A, inflation, Thiel of semester. That's nice. This is the, and now we have to dualize. Then nabla m is equal to what? To the proper standard model of M dual dualized. And so this is equal to what I write just before. I have to put it here. I will write in another color. We put this here and dualize. And when we dualize, A op go to A. That is because the positive of the positive is just the algebra of the beginning. So this is the proper standard model, the proper co-standard model. We have to, it's a little bit confused how to construct it, but it is very useful. There is some question. If there is no question, I will write here, state some lemma that I didn't prove. I will not prove it. It is very useful. Is that it says that the functor delta and nabla are exact functors. And this is a very important property of functors between abelian categories. And then and now I will state the other part of the theorem 313 that we proved yesterday. You can fix it here. Yesterday we proved this theorem 313, which asserts that the head of the proper standard modules are simples. They are the L lambda, and they give a classification of the simple model of the A. Now, in the case of the proper standard model, they say more or less the same, but instead we have to take the circle. This is the statement, the more precise statement. If lambda is a simple T module, then the circle of the proper co-standard model of lambda is isomorphic to L lambda. So it is simple, and it's isomorphic to the to L lambda, which I recall it is the head of the proper standard model. So this gives us another way to construct the simplest A model. And we don't do the proof. I just mentioned idea of the proof. Dualize is more or less like dualize the results proved for the proper standard models. More or less like as dualizing and using the property of this factor, one can prove that it's called, and but that is enough for us. Are there some questions? Okay, no question. Everybody hear me well? Yes. Okay. Now, so we now we will prove our next objective is to prove what is called Brouwer reciprocity. Brouwer. And this Brouwer reciprocity gives us very good information about the category of A modules, and for proven and for stated this reciprocity, we need both objects, the proper standard and the proper co-standard modules, and also what we call now standard objects, which are these are constructed in the same way, but instead taking using the simplest model, we will use projective models. So I need to introduce some new definitions. So notation. A and lambda will be as before. And we will say that we denote P sub t of lambda. This denote the projective cover of lambda in CT, in the as T models. And also we need to introduce the injective hull, which is we will denote IT lambda. This will be the injective hull. In the category of T models. and after we have the simple object are the first main information about the category of model, and then when the algebra they are not semi-simple, the other objects which follow in as they are important in the category are the projective and the injective. For this reason, we will consider them, and we will consider the projective cover of L lambda. So we will denote P lambda without T. This is projective cover. Denote the projective cover so projective, write smaller, of L lambda in the category of A modules, and I lambda is the injective hull of L lambda. It's the category of A models. This is just a notation. Now appears a new definition. Definition. For lambda and lambda. Now delta lambda without the bar is the proper standard model of the projective cover of lambda in the category of T model, and we will call this a standard model. This is the standard model of lambda. And nabla lambda. This is a definition. It's nabla bar of the injective. It's the co-standard model of lambda. And okay, some remark. We have that because these functors that we introduced, the lambda bar and nabla bar, delta bar and nabla bar, we have a projection from lambda, from the standard to the proper standard, and we have an inclusion from the proper standard, proper co-standard to the standard, the co-standard. And if T is semi-simple, T is semi-simple, we have that the projective cover of lambda is equal to lambda and also equal to the injective hull. So in this case, lambda bar and the proper standard and proper co-standard are equal to the standard. This is just a remark. Yes, until here we have just the definition. I will introduce in a second a new definition, which is more, but that is for now. There is some question. Are there some questions? Can you fix there? So I need to introduce and read a new definition. Another definition, which is related with these proper standard models. Let for if we have a model in the category of A models, we say that M admits a standard filtration we say that a model admits a standard filtration if there exists a filtration in the category of A models. M, this is the filtration. Such that the quotient, this successive quotients, is isomorphic to a standard model. For some lambda e in simple over T, and for all I. This is similar to the filtration that mentioned before, where the quotient was simple T model, but here we want that the quotient has to be a standard object, the standard models. And we will denote C lambda 8 to the category of a standard object, of a standard filtered object. Okay, just to for instance, let me see what happened is S is 2, for instance. For instance, if S is 2, this means that M has a submodule M1 isomorphic to delta lambda for some lambda such that when you quotient M by M1, this is isomorphic to L mu for some mu simple over T. Or we can write our equivalently. There is an exact sequence there is an exact sequence of in this way. So it's like this standard model. Okay, the model. We can say that more or less that the module admitting and a standard filtration can be constructed using a standard model. That is what we are saying here. As in the same way as for composition factors, when we consider, maybe I put here, in the category, every module can be constructed as a extension of simple models. We here are concentrated in the case of the module which can be constructed as an extension of a standard models. And what we will see is that every projective module can be constructed using standard models. This will be a corollary of the lemma. So now I will state a lemma which will be useful in order to prove the Brouwer reciprocity. Are there some questions before I continue? Okay. So let me state the lemma. This is lemma 4.3. And this say that we consider the standard module of lambda. So let lambda in a simple module as a B minus module. When we consider the restriction, this is projective, is the projective cover of inflation. So all this is in the category of B minus models. The second part of the lemma say that the X groups between the standards and proper co-standards these are the field or zero, and it's the field only if lambda is equal to mu and n is equal to 0, and otherwise all these are 0. Just in a second. This lemma is we have more points, but for that, if you don't know what is the X group, I only say that it is now I will write something, but it's very important in order to obtain information about the category of model, because they measure the extension between the object that we put here. And just in a moment I will write something, but let me continue with the lemma. The third part of the lemma say that if M admits an standard filtration, I will call that C delta means the models which are meet standard filtration, then we will prove that then the restriction when we see M as a B minus module is projective. Is projective in the category of B minus model, because we are taking the restriction. And the last point of the lemma is say that if M is a graded model over A and the restriction of M when we see, if we see that M as B minus model is projective, then M admits a standard filtration as a graded model. Now we can write a corollary of this. Yes. So this is all the lemma, and I would like to write here now a corollary for to say that if M in the category of grade or is a module over H which is projective, then this module admits a standard filtration. So a corollary of this lemma ensure that every projective module over A admits a standard filtration, or in other words, we can construct the projective modules of A as an extension of standard models. And this is the reason because why these standard models are so important. One of the reasons we can construct them, we can use them in order to construct projective modules over the algebra. Are there some questions? I would like to write a remark about the lemma. Just in order to say something about this X group, I would like to say that X gives a measure of the extensions between M and N. This is for any category of model. Just in order to have an idea what is X, because we don't have time, if you don't know what is X, we don't have time to introduce this X group, but it's maybe this give you a motivation to go to a book and learn about them. It appeared in this book of Curtis and Reiner that I sent you yesterday. For instance, X 0 when N is 0, M and N, this is the Hopf space. This is just the space of morphism between M and N. And if you consider X1, this classify the extensions or the short extensions. So it classified this X1, classify all the objects, all the modules X, which fits in an exact sequence like this. So for this reason, these X group are important and give very good information about the modules. And what say the lemma, you return to the lemma, to this part of the lemma. The lemma say that there is not extension between the standard and proper to a standard model. So it's that we cannot put nothing between them. This so this proper standard and the standard and proper co-standard give allow us to control the category in some way. Are there some questions? I would like to try to prove something of this lemma before to the end. We have 10 minutes. I think we can do something. So we will start with the proof. We will start with the first part. And okay, and before I start with the proof, let me say that the Bragg reciprocity that I will state tomorrow and prove it. What say this reciprocity? They compare the number of standard of the composition factor of a standard module and the quotient or the subquotient of a standard filtration. We will see how they are related tomorrow through the Bragg reciprocity. So let me start with the first part of the lemma, which say that when we see the standard module of lambda as a B minus module, then it is the projected cover of inflation of lambda. So first, we see that, we recall that when we restrict to B minus, this is equal to B minus tensor T projective of lambda. This is because of the lemma 3.8. Because here the standard of lambda is the proper standard of this projective module, so we can use lemma 3.8 to see that as B minus module we have this isomorphism. and thus then it is projective. Because this also is projective. And the properties of a property of tensor T. This you can see a proof of when you induce from a projective module, you will obtain a projective module. That is the reason, because this is projective. You can see a proof of this in the book of Curtis and Reiner. And also it's a nice exercise if you want to practice the definition of projective modules. Okay, then the other thing that we have to prove, we just proved that it's projective. We have to prove that it's a projective cover of inflation. That means that we have to prove that the unique simple quotient of this module is inflation. And we will do this in the same way that we proved yesterday, that an analogous result for the proper standard module. So we must prove now that lambda inflation is the unique simple quotient. And this follows, or we will argue as in the proof of lemma of the theorem 3.13. Here I will write. We will use the Hopf. We will compute the morphism. What we will have to do is to compute the morphism as B minus module between restriction of the standard module and inflation of any other U. So I see I recall that we used the same idea when we proved that not the standard, if not the proper standard with the bar up over delta. We used this to compute the Hopf. Okay, and the first thing that we have to do is to change the restriction using this isomorphism. Using this isomorphism, we can put here P minus T P. Okay, that here I am using this. And next, we used again the Frobenius reciprocity. This is isomorphic to the Hopf as T module between Pt lambda, and we can put mu. That is the Frobenius reciprocity that I mentioned yesterday also. So this is why we can put this here. And now, as this by definition is the projective cover of lambda, this is the field, or it is zero. If the field, if lambda is mu, or zero otherwise. And this is because it's the projective cover of lambda. We have defined this in this way. So, okay, and this said us that the only way that what we proved that between the standard module as B minus module and a simple module over B minus, there is only a morphism when mu is lambda. So this means that this simple module is a quotient of this one only when mu is lambda. So this means that inflation of lambda is the unique simple quotient of the standard module as a B minus module. This completes the proof of the part A. So this completes of A. Okay, and I think we will finish here, and tomorrow we will complete the lemma, the proof of the lemma, and we will complete and we will state and prove the Frobenius reciprocity, and we will give some examples of Hopf algebra with triangular decomposition. That will be the end of the course.